Welcome. This is a brief description of our project titled Reinforcement Learning of Social Distancing During COVID-19 with a Confounder. The idea of this project is to serve as an exploration of the effects of a confounding variable in the reinforcement learning setting. To illustrate this, we chose to use a relevant example, the effects of social distancing policy in the spread of COVID-19 on different communities. In order to simulate the spread of COVID-19 for the purposes of building an environment to do reinforcement learning, we settled on the use of an SEIHRD epidemic model. It is a system of differential equations that models the spread of the virus by describing the dynamics of transition between the successive states of the disease in a group of agents. These states include susceptible, exposed, infected, hospitalized, recovered, or dead. The direction of transition between the states is outlined in the diagram currently on display. For the action space of our environment, we chose to adjust the beta parameter, which governs the rate of transition between susceptible and exposed, to a particular percentage at any given time. The 5 percentages we chose to operate are 0, 10, 25, 50, and 100%. To illustrate the effect of social distancing with the sole aim was to reduce the number of deaths, we used the following as a reward function. The value of the individual is multiplied by the number of susceptible individuals minus the number of deceased individuals. The following curve shows the effects of using a static policy over our range of possible actions across the whole simulated epidemic for a number of different measure factors. We can see that the spread of the disease illustrated in the exposed, infected, and hospitalized graphs. As we can see, with no associated costs for implementing social distancing, the best option is to use it to perform 100% social distancing. This ensures that nobody transitions beyond the susceptible stage and has the highest reward. However, for more practical policies, we can observe that even differences from 10% to 25% social distancing flattens the curve significantly more. We now wish to demonstrate the effects of an unobserved confounder on reinforcement learning. In the example that follows, we have a location as an unobserved confounder. Our action space still remains the same, the strength of social distancing applied to the environment. However, we now introduce two new variables to an environment: the non-adherence factor and economic cost of social distancing. Non-adherence is the amount of social distancing policy violation in a given environment, while the economic cost of social distancing represents the lost economic output as a function of the amount of social distancing applied. The non-adherence policy is implemented by multiplying the current social distancing policy by 1 minus n, where n is the non-adherence factor. The economic cost of social distancing is implemented by subtracting the product of an economic output factor by the current social distancing policy being enforced. To present a clear picture, we have two simplistic examples: Tech Haven and Steeltown. Tech Haven has a high economic contribution per capita due to the nature of the work transitions to remote work are easier to implement, thereby ensuring workers adhere to social distancing policies without much effort on livelihood. This location would have a high adherence to social distancing policies, but also a high cost of social distancing. Steeltown is a manufacturing city, where economic outputs per capita is comparatively low. Steel plants play a central role in the economy, making remote work impossible and forcing workers to rely on a daily wage to make ends meet to go into work, thereby violating social distancing policies. This location would have a lower adherence to social distancing policies, but low cost of social distancing. We will explore the effect of the confounder by first artificially fixing the value, thereby indirectly adjusting for the given level of confounder, and then having it vary probabilistically. We expect to see that when we fix the level of the confounder, our agents will learn an optimal policy for the given level of confounder. However, in real life, we do not have a way to adjust for a casual confounder in reinforcement learning. Therefore, the policy learned when we don't account for the confounder will do disproportionately worse than the adjusted policies in these environments. By using the policy gradient algorithm to train our policy, we can see that the anticipated. Our agents learned that the best policy for Tech Haven is to perform almost no social distancing. It also has the highest reward among our static policies. We can also see that for Steeltown, our learned policy balances the curtailing the spread of COVID with low economic cost of implementing social distancing, to implement a policy that's almost 100% social distancing, but realistic in allowing for some economic contribution. We can see from these reward plots a confounded policy that does not adjust for casual confounder does disproportionately worse than policies trained in fixed levels of confounder for both Steeltown and Tech Haven. This is just an interesting area of exploration in reinforcement learning, studying the causal structures of problems to help optimize for decision making.